Hello, and thanks for checking out Chemistry Connections on the Hopewell Valley Student Podcasting Network, a proud partner of hvspn.com, where students come together to publish content to share with the world. The opinions represented within this episode are those of the content creators only. Please enjoy the show.
Welcome to Chemistry Connections.
Our names are Lucy
and Jack, and we are your hosts for episode 11, called The Chemistry of Ice Hockey. Ice hockey is one of the greatest sports to both play and watch. It features extremely fast-paced and physical gameplay because it's played on ice. Hockey originated in Canada during the early 1800s, and it comes from the French word hocquet, meaning stick.
The game involves one goalie and 5 other players who skate around trying to score goals. One of the greatest sporting achievements ever, the Miracle on Ice, was an Olympic ice hockey game where the underdog U.S. men's team beat the top-seeded USSR team. This illustrates the elusive nature of hockey and the unpredictability surrounding it, drawing fans from all around the globe.
So, Lucy, why are we talking about hockey today?
Well, both of us adore sports. Hockey has been a key aspect of my childhood in a way I've connected with my dad and other people in my family.
And my next up for me after high school is I hope to become a professional sports commentator. So it was only natural for both of us to reach the chemistry and science behind a sport like hockey.
Let's pause here to talk about some chemistry at work. We'll be covering the most important aspect of hockey, the ice, but let's put a pin in that first. Because first, we'll be discussing the pucks that slide across the ice.
So Lucy, what is it about ice hockey pucks that make them different from any other old disc of rubber?
Well, ice hockey pucks are made out of vulcanized rubber. Vulcanized rubber is used to create O-rings, tires, and much more. Its unique properties make it a useful tool in not just ice hockey. Before the process of vulcanization was developed, rubber was susceptible to changes in temperature. If it was too hot out, the rubber would quickly melt, or if it was too cold, it would become brittle and break.
I bet you that the rubber was often too cold in hockey.
Totally. Thus, vulcanization is an important part of what makes ice hockey pucks work. Vulcanization works by forming chemical crosslinks or covalent bonds,
which are attractive forces between nonmetal atoms.
These form between long isopropene molecules,
which is a natural rubber monomer, aka a carbon chain,
using sulfur. This Venn diagram looks like long carbon chains parallel to each other. Then they are connected by perpendicular bonds with sulfur. This forms a net-like structure which contributes to the hockey puck's key characteristics:
resistance to extreme temperatures and strength.
This allowed Alexander Rizantsev from the KHL, a Russian pro league, to hit a slap shot at 114.27 miles per hour, which is the current world record.
That is incredibly impressive. I think I could hit one probably about 60 miles per hour, and I would top out around there, especially if I had to do it on ice. I think I would fall. More important to the hockey than the pucks is the ice. I mean, it's hockey's defining characteristic. It's what makes it different from all other sports.
And cooler and better and more fun.
Yes. This contributes to super fast gameplay, and everybody gets to wear cool skates. Now, ice, as we all know, is made of water. The intermolecular forces, or IMFs, are attractive forces between particles. The IMFs between water molecules are known as hydrogen bonds. They're the strongest form of bond, and they occur when hydrogen atoms in a molecule bond with nitrogen, oxygen, or fluorine. The result is that it requires a lot of energy to break these bonds. In our case, we're talking about melting the ice, making it go from solid to liquid. Hydrogen bonds aren't the only IMFs between water molecules. London dispersion forces exist between all particles, but they are weaker and they're not as strong as the hydrogen bonds, which is what we're mainly going to focus on today. The best part about going to see a hockey game, in my opinion, I don't know, you may have different opinions as a huge fan of the sport, but my favorite part is the Zamboni. The Zamboni is this really big machine that comes out in between periods or during the intermission to clean and smooth the ice.
And it looks really, really cool. I mean, really, really cool. Did you know that when you go to a pro game and it's your birthday, a bunch of little kids ride around on it?
Would they let an 18-year-old adult ride around on the Zamboni?
I hope so, because I really want to.
I think we should make that our goal. But Zambonis start by scraping away the top layer of the ice. There are still lots of deep grooves in the ice from the skaters after that, though. In order to fix this, the Zamboni lays down a piping hot layer of water. Now, that may seem counterintuitive. Hot water on the ice? What's that going to do? Melt the ice? Yes. The water transfers heat into the top layer of the ice, which causes the hydrogen bonds between the water molecules to break because of how hot it is. This melts the ice and gets rid of the grooves. The Zamboni then has a broom behind it, which smooths the water out, making it a safe skating surface again. Then, because the whole arena is cold and sitting on top of a giant sheet of ice, the thin layer of water cools at an extremely quick rate and it refreezes. The ice is the defining feature of hockey, and knowing how it works and how the Zamboni works can enhance our love for an already really cool sport.
It was so much fun learning about the chemistry of ice hockey today.
I think I'm going to have to watch more hockey in the future and maybe learn to announce it a little bit,
And hopefully ride a Zamboni.
Thank you for listening to this episode of Chemistry Connections. For more student-run podcasts and digital content, make sure that you visit www.hvspn.com.